Nothing was heard at the moment everything was born: space, time, and matter. This audiobook invites you to explore a surprising paradox. How can the greatest event in the universe have been completely silent? Forget the image of a thunderous explosion. The Big Bang was not like how it is portrayed in movies. Discover why the origin of the cosmos occurred without a single sound, and what that reveals about the true nature of the universe. Imagine a moment when everything we know began to exist, an explosion of energy and matter, the creation of time and space. However, in the midst of this cosmic catastrophe, there is no sound. How can this be possible? To understand it, we must first delve into the concept of the Big Bang, the theory that describes how the universe began. But what about acoustics in this context? Why does sound, something so omnipresent in our daily lives, disappear in the vast emptiness of space? When we think of sound, we generally associate it with vibrations that travel through a medium, whether air, water, or even solids. But here lies the first key. Sound needs a medium to travel. Have you noticed that when you dive into water, sounds feel different? This is because water is a denser medium than air, which changes the way we perceive vibrations. Now imagine outer space, where air and other media are absent. In that vacuum, sound simply cannot exist. The expansion of the universe was a violent and tumultuous process. After the Big Bang, everything began to move away at an unimaginable speed. But what happened to sound waves in that context? As the universe expanded, it cooled. And here arises another intriguing question. How did temperature conditions influence sound production? In the early moments, the universe was an extremely hot and dense place where particles collided frantically. However, as it expanded, those conditions changed drastically, creating an environment that was not conducive to sound propagation. At a critical point known as the era of recombination, matter and radiation began to decouple. This was a decisive moment in the history of the universe, but how does this relate to the silence surrounding the Big Bang? During this period, the universe became transparent to radiation, but the ability to generate sound was no longer present. The acoustic waves that might have existed in the primordial plasma did not translate into audible sounds. It's as if the universe decided to keep its secret in profound silence. Now imagine there is an echo of those early moments, a trace of what occurred. The cosmic microwave background radiation is like a recording of those initial instants. But it is not sound, it is light. Its discovery was a milestone in cosmology, revealing crucial information about the origin of the universe. But what does this tell us about the absence of sound? Throughout our history, we have witnessed cataclysmic events in space, star explosions, and galaxy collisions. In those moments, sound also behaves differently. So why can't we hear the Big Bang? The answer lies in the very nature of sound and the way we perceive it. When we talk about sound, we refer to human perception, to how our ears translate vibrations into something meaningful. The science of acoustics in space has advanced, but there is still much to discover. Scientists conduct experiments and simulations to understand how sound behaves in the cosmos. However, the reality is that many of these explorations are limited by the conditions of the vacuum of space. It is a world where silence reigns, and where sound waves, although fascinating, remain trapped in a maze with no exit. The silence of the Big Bang also leads us to reflect on our existence. If the universe began in silence, what does that mean for us? It invites us to question our relationship with the cosmos. Are we truly alone in this vast universe? The lack of sound suggests that despite the immensity of what surrounds us, there is a profound mystery that we have yet to unravel. As we look to the future, it is exciting to think about how research on sound in the cosmos will continue to evolve. Each discovery brings us one step closer to understanding not only our origin, but also our place in this ever-expanding universe. Thus, the story of the silence of the Big Bang becomes a journey into the unknown, where each question leads us to new answers. Finally, the silence of the Big Bang is a reminder that sometimes the deepest answers are found in the least expected places. In a universe that began in complete silence, there is an intrinsic beauty in the mystery and in the quest for answers. And you, what do you think about the meaning of that primordial silence? The Big Bang is a fascinating concept that has captured the attention of scientists and curious minds alike. But what is the Big Bang really? In simple terms, this theory describes the origin of the universe as we know it. Imagine a tiny point, a space smaller than an atom. In an instant, that point exploded, giving rise to all the matter and energy that form our universe. But how do we know this actually happened? The answer lies in the evidence that has been collected over decades of research. One of the most compelling pieces of evidence for the Big Bang is the expansion of the universe. When observing galaxies, astronomers noticed that they were moving away from each other, as if they were in some sort of cosmic race. This can be compared to an inflating balloon. As you blow it up, the points drawn on its surface move away from each other. This expansion is due to the energy released at the moment of the Big Bang, and it is one of the pillars that supports this theory. Now let's take a moment to think about what expansion means. It's not just a matter of space, it also involves time. When we say the universe is expanding, we are talking about a process that has lasted billions of years. With each passing second, the universe expands a little more. But what about sound in all of this? If the Big Bang was so powerful and explosive, why don't we hear anything? To understand why the Big Bang was silent, we first need to define what sound is. Sound is a vibration that travels through a medium such as air, water, or even solids. It is something we perceive thanks to our ears, which detect these vibrations. But this is where the story gets complicated. In space, there is no air or water, so sound as we know it cannot travel. Imagine you are in a room full of people all talking at the same time. The noise is deafening, and you can hear your friends without any problems. Now, if you suddenly find yourself in the vacuum of space, that same conversation becomes inaudible. Without a medium to propagate those vibrations, sound is drowned in the silence of the cosmos. This is how the Big Bang, despite its immense energy, was a silent event. The expansion of the universe also plays a crucial role in this silence. Right after the Big Bang, the universe was extremely hot and dense, filled with particles interacting frantically. As the universe expanded and cooled, these particles began to group together, forming atoms. In this process, conditions were created that did not allow sound to be transmitted in the way we understand it. In other words, the universe was becoming quieter as it expanded. Still, that doesn't mean there couldn't have been vibrations in that primordial plasma. In the early stages of the universe, acoustic waves might have existed, but not in a form that our ears could detect. These waves were different, more like the movement of an ocean of energy rather than the melody of a symphony. So while there might have been sounds, they were not sounds in the conventional sense, but rather vibrations that did not translate into hearing. As the universe continued to expand and cool, a crucial moment known as the era of recombination arrived. During this period, electrons and protons combined to form atoms, allowing light to begin traveling freely. But again, at this critical moment, the conditions were not suitable for sound to exist as we understand it. Matter and radiation decoupled, creating a silence that endures to this day. Cosmic background radiation is another fascinating aspect that helps us understand the Big Bang. This echo of the past which fills the universe is the trace of that initial event. It was discovered in 1965 and represents a kind of whisper of the Big Bang, but not a sound in itself. The background radiation can be imagined as the warmth you feel when you approach a campfire, but without hearing the crackling of the wood. It is a manifestation of the energy that remained after that silent explosion. Throughout the history of the universe, there have been other cataclysmic events, such as supernova explosions, that do generate sound, but in a completely different context. In those cases, sound travels through media like gas and dust in nebulae. Comparing these events to the Big Bang helps us understand even more how sound behaves in the cosmos and why the Big Bang was a unique experience in its silence. The human perception of sound also plays an important role in this discussion. Our ears are designed to pick up vibrations in a medium, and that has shaped our understanding of the world. However, in the vast universe where silence predominates, our auditory capabilities are limited. What does this mean for our existence? The absence of sound in the Big Bang can lead us to reflect on the nature of the universe and our connection to it. It is fascinating to think about how scientists study sound in space. Despite the limitations of the vacuum, they use simulations and mathematical models to understand what those vibrations might have been like in the early universe. Thus, the science of acoustics intertwines with cosmology, opening new doors to the exploration of the cosmos. In a world where sound and light are different yet complementary, the relationship between these two forms of perception becomes essential. The electromagnetic waves we capture through telescopes can offer a view of the universe that goes beyond what our ears could hear. It's as if the universe speaks in a language we are just beginning to understand. Myths and misunderstandings about the Big Bang and sound are common. Many people think the Big Bang was like an explosion that made noise. But the reality is much more subtle and complex. Clarifying these misconceptions is fundamental to appreciating the beauty and mystery of the universe. The silence of the Big Bang is not a lack of sound, but an opportunity to explore the depth of what it means to be part of a cosmos that, at its essence, began in profound silence. If you're enjoying this journey through the universe and want to keep exploring more cosmic mysteries, don't forget to subscribe to the channel and give the video a like. Thank you for being part of this Star Odyssey. Sound is one of those everyday wonders that surround us, from the singing of birds in the morning to the murmur of a conversation in a cafe. But have you ever wondered exactly what sound is and how it is produced? To understand it, it is helpful to imagine it as a series of waves traveling through different mediums. Essentially, sound is a vibration that propagates, and these vibrations can occur in air, water, or even solids. But what does this mean in simple terms? When you speak, your vocal cords vibrate, creating pressure waves in the air. These waves move through the air molecules around you, pushing and stretching them as they go. It's like throwing a stone into a calm pond. The waves that form on the water's surface are analogous to how sound propagates in the air. Every time an air molecule moves, it pushes the next one, and so on, until the sound reaches the ears of the listener. The nature of sound is fascinating, but not all sound waves behave the same way in different media. For example, in water, waves travel faster than in air. This is because water molecules are closer together than air molecules, allowing the vibration to be transmitted more efficiently. Imagine you are in a pool and someone jumps in. You can feel the waves generated in the water immediately, unlike what would happen if you were in an open field. However, what happens in the vacuum of space? This is where the story becomes even more intriguing. Space is a place where there is no air, which means there is no medium for sound to propagate. So if you were floating in space and shouted, no one could hear you. It's a difficult concept to process because we are so accustomed to hearing sounds in our environment. In the vacuum, sound becomes a mystery, a phenomenon that cannot exist without a medium to carry it. The expansion of the universe after the Big Bang also plays a crucial role in how we understand sound. In its early moments, the universe was extremely dense and hot. In that environment, sound waves could have been created. But as the universe expanded, that density decreased. The expansion not only affected matter, but also influenced the possibility of sound waves developing in ways we could understand. Imagine a balloon that you inflate. At first, the air inside is dense, but as you keep inflating, that air disperses. Similarly, the universe began as an extremely dense point that expanded, which had a direct effect on how sound waves were produced and propagated. The temperature of the early universe, which was incredibly high, also affected the types of vibrations that could occur. In those early moments, the universe was a place filled with hot plasma, a state of matter where electrons are separated from atomic nuclei. This mix of energy and particles could have generated acoustic waves, although not in the sense we understand today. Acoustic waves in a plasma do not translate into audible sound for our ears, but they do represent a vital aspect of how the universe behaved in its infancy. Now, what about the era of recombination? This was a crucial period when matter and radiation decoupled, allowing photons to move freely. This means that, in a sense, the universe became silent. The matter that was once so tied to radiation separated, and the conditions changed in such a way that sound waves could no longer propagate as before. It is a moment in the history of the universe that helps us understand why the Big Bang was silent. The cosmic microwave background radiation, which is the echo of the Big Bang, also gives us clues about this silence. Discovered in 1965, this radiation is a remnant of the heat of the early universe. Although it is not sound, it is a form of energy that tells us about what happened in those initial moments. It's like having a recording of an ancient event, but without the clarity of audible sound. The sound waves in the early universe, therefore, become a mix of vibrations that we do not hear, but which were fundamental to the formation of cosmic structures. Through simulations and studies, scientists have been able to detect these waves and understand their importance. But how does this relate to other cosmic phenomena? The physics of cataclysmic events, such as supernova explosions, shows us that sound behaves differently in space. In those events, although sound does not propagate as it does on Earth, the energy released can create shock waves that behave in surprising ways. It is an interesting contrast to the silence of the Big Bang, where there was no medium for those sound waves to form at all. The human perception of sound is another fascinating aspect. Our ears are designed to capture sound waves within a specific range of frequencies, allowing us to interpret the world around us. But what happens when we consider a universe that began in silence? The lack of sound in the initial moments invites us to reflect on how our perception is intrinsically related to existence itself. What does it mean for us as human beings that the universe at its origin did not emit a single sound? Finally, the science of acoustics in space remains an exciting field of research. Scientists continue to explore how sound can be studied in space, using experiments and simulations to better understand how sound waves behave in different environments. As technology advances, so does our understanding of how these waves can reveal secrets about the cosmos. All of this leads us to an inevitable conclusion. The silence of the Big Bang is not just a curious scientific fact, but a window into the complexity of the universe. It invites us to question our understanding of sound and the way we perceive the world. Thus, the exploration of sound and its relationship with the cosmos becomes an ongoing mission, where each discovery brings us one step closer to unraveling the mysteries of our origin. What is really in the vacuum of space? To understand the silence that reigned in the universe after the Big Bang, it is crucial to explore the concept of vacuum. Many think of vacuum as a simple nothingness, but in reality, it is a space full of possibilities. In the universe, vacuum is not simply the absence of matter. It is an environment where pressure is extremely low, where particles are scarce, and where conditions are very different from what we experience on Earth. Did you know that sound, as we know it, needs a medium to travel? In our daily lives, sound propagates through air, water, or even solids. Think about how you hear a bird singing. The vibrations produced by its song travel through the air and reach your ears, allowing you to enjoy that melody. However, in space, where vacuum predominates, there is no air, no water, or anything that can carry those vibrations. So what happens to sound in space? Imagine an orchestra in the middle of a desert. Even though the musicians play with all their hearts, the sound would get lost in the vast silence. This is exactly what happens in space. Sound waves simply cannot propagate in a vacuum because there are no molecules to vibrate and transmit those waves. This is a fundamental concept for understanding why the Big Bang was a silent event. The expansion of the universe after the Big Bang also plays a crucial role in understanding sound. In the moments following this event, the universe began to expand at an incredible speed. This phenomenon, known as cosmic expansion, means that the distances between objects in space are constantly widening. Imagine throwing a stone into a pond. The waves that form disperse as they move away from the point of impact. In the universe, that expansion causes any form of sound to move away and dissipate into the vast vacuum. Moreover, the temperature of the primordial universe was extremely high. In those early moments, the universe was filled with a hot and dense plasma. In such a medium, sound waves could have been generated, but the nature of space and the subsequent expansion meant that those waves did not translate into audible sounds. It is fascinating to think that although sound could have existed in the form of waves in that plasma, we would have no way to hear it. As we reached the era of recombination, the universe underwent a drastic change. As matter and radiation began to decouple, the landscape of the cosmos changed even more. At this point, the plasma cooled, allowing electrons to join atomic nuclei and form atoms. But what does this mean for sound? The creation of atoms meant that the medium for transporting sound waves was present, but the vacuum of space remained an obstacle. Thus, the possibility of hearing sound in the universe faded away. However, not all is lost. In the early universe, acoustic waves may have emerged in the primordial plasma. These waves were different from what we know as audible sound, but their existence is a testament to how the universe was full of activity. Density fluctuations in this plasma would have created patterns that, although we could not hear, are essential for understanding the evolution of the cosmos. The cosmic microwave background radiation, an echo of the Big Bang, provides us with a window into those early moments of the universe. Discovered in 1965, this radiation is like a photograph of the universe in its infancy. Although it is not sound, it is a representation of the energy and conditions that existed at the time of the Big Bang. This radiation speaks to us of a time when the universe was a completely different place, full of heat and activity. By observing other cataclysmic events in the universe, such as supernova explosions, we can once again see how sound behaves differently in vacuum. On Earth, an explosion generates sound waves that we can hear. However, in space, those explosions become bright lights and energy that travel through the vacuum, leaving behind the ability to hear the roar that accompanies them. The human perception of sound is another fascinating aspect. Our ears are designed to capture vibrations in the air, but if sound cannot travel in space, how does this affect our understanding of the cosmos? Hearing is fundamental to our experience of the world. And the fact that the universe began in silence raises questions about how we interpret what lies beyond our planet. The science of acoustics in space is a growing field. Scientists are conducting experiments and simulations to better understand how sound works in different environments. Through this research, they aim to unravel the mysteries of the universe, even regarding acoustics. Each discovery brings us one step closer to understanding the silence surrounding the Big Bang and the events that have shaped our cosmos. Electromagnetic waves and sound waves are different but complementary in the exploration of the universe. While sound needs a medium to travel, light can traverse the vacuum of space. This duality offers us powerful tools to study the cosmos and decipher its secrets. What would a conversation between sound and light tell us about the origin and evolution of the universe? The silence of the Big Bang should not be seen as a lack of activity, but as a reminder of the complexity and wonder of the universe. The waves that could have existed in that primordial moment connect us to our cosmic history and show us how we have come to where we are today. This silence invites us to reflect on our relationship with the universe and what it means to be a part of it. Finally, when considering the future of the study of sound in the cosmos, it is exciting to imagine what is still left to discover. As technology advances and our methods of exploration become more sophisticated, more questions will be answered. The silence of the Big Bang has left us a legacy of mystery that will continue to inspire generations of scientists and thinkers to come. The reality is that the universe began in silence. But that does not mean it is devoid of stories to tell. Each discovery about sound and vacuum brings us one step closer to unveiling the secrets that have been hidden since the beginning of time. In this journey toward understanding, silence becomes a powerful reminder of the beauty and complexity of existence itself. The expansion of the universe is one of the most fascinating ideas that has emerged in the history of cosmology. To understand its impact, it is crucial to imagine how it all began. What happened just after the Big Bang? The answer is not simple, but we can visualize it. Imagine a balloon being inflated. As you blow air into it, it not only expands but also stretches. Similarly, the universe also began to grow, to expand from an incredibly dense and hot point. But what does this expansion really mean? In simple terms, it means that galaxies and stars are not static in space. Instead, they are moving away from each other. This idea is based on the observation of a phenomenon known as redshift. When astronomers look up at the sky and analyze the light from distant galaxies, they notice that this light shifts to longer wavelengths, as if the galaxies are fleeing from us. This phenomenon is a key clue that confirms that the universe is not only expanding, but has been expanding since its inception. Now let's return to the moment of the Big Bang. The expansion of the universe did not just create space, it also generated conditions that impacted the behavior of everything that formed within it. At that initial stage, the universe was an extremely hot and dense place, where matter and energy were mixed. But as it expanded, this heat began to dissipate. What effect did this have on sound? To understand it, we must first remember that sound needs a medium to travel. On Earth, sound moves through air, water, and even solids. But what happens in space, where vacuum reigns? In the vacuum of space, sound simply cannot propagate. There are no air molecules to vibrate, no water to transmit the waves. So, in the context of the Big Bang, as the universe expanded and cooled, the ability to generate sound became increasingly limited. But does this mean that there were no sound waves at all? The answer is more complex than it seems. During that initial expansion, although sound as we know it could not exist, acoustic waves were generated in the primordial plasma. This plasma, a hot soup of subatomic particles, could vibrate in ways very similar to how sound does on Earth. The expansion of the universe not only meant that sound could not travel, but it also shaped the creation of cosmic structures. Galaxies, stars, and other celestial bodies began to form as the universe cooled and particles started to group together. But how does this relate to sound? The waves produced in the primordial plasma helped shape the distribution of matter in the universe. So, although we do not hear a noise from the Big Bang, those vibrations contributed to the formation of the cosmos as we know it. As the universe continued its expansion, the temperature kept dropping. This was crucial for what happened next. Conditions became more favorable for the formation of atoms and subsequently molecules. But during this process, sound remained out of our reach. The temperature of the early universe was so high that any attempt at sound quickly turned into energy, leaving no trace of what we might have heard. Over time, the universe reached a crucial stage known as the era of recombination, when matter and radiation decoupled. At this point, hydrogen and helium atoms began to form, allowing light to travel freely. But in this vacuum, sound still had no place. The absence of a suitable medium meant that the propagation of acoustic waves remained impossible. However, we cannot help but wonder if sound waves existed in the early universe. Although we could not hear them, there were indeed vibrations in that primordial plasma that, while inaudible, played an important role in the evolution of the universe. These sound waves became patterns that influenced the distribution of galaxies and matter on a large scale. Therefore, although the Big Bang was silent, its echo is felt in the structure of the cosmos. Cosmic background radiation is another fascinating aspect that arises from this context. By studying this radiation, scientists can gain valuable insights into the events that occurred during those early moments. This radiation is like a fingerprint of the Big Bang, a remnant of the heat and energy that once filled the universe. Even though there is no sound, understanding these phenomena helps us unravel the mysteries of our origin. As we explore more about the expansion of the universe, it is interesting to think about other cosmic phenomena. For example, supernova explosions are violent events that produce shockwaves. But what about sound in those contexts? Although the vacuum of space remains an obstacle, the energy released in those events is a reminder that the universe is full of activity. Even if we cannot hear it, the human perception of sound also plays a role in our understanding of the universe. We like to think of sound as a form of communication and connection. However, the silence of the Big Bang invites us to reflect on the nature of the cosmos and our relationship with it. If the universe began in silence, what does this mean for our existence and our quest for answers? Perhaps silence is as significant as any sound. Ultimately, the expansion of the universe teaches us that, although there may be no sound as we know it, there is a symphony of cosmic processes that shape the reality in which we live. The science of acoustics in space continues to evolve, allowing us to explore how sound waves behave in different contexts and how this knowledge can be applied to our understanding of the cosmos. So, although the Big Bang was a silent event, exploring its impact provides us with a fascinating journey through the history of the universe, where each discovery brings us closer to understanding the incredible complexity of existence itself. The expansion of the universe not only changed the cosmic landscape, but also invites us to keep questioning and exploring the mysteries that still surround us. How was the universe in its early moments? The answer to this question takes us to a truly extraordinary instant, a time when conditions were so extreme that our current understanding of physics could barely be applied. In this context, the temperature of the early universe was incredibly high, reaching billions of degrees. But what does this really mean in terms of sound, and how does it affect the way we understand the Big Bang? Imagine that we are in a gigantic pressure cooker. In this place, particles are so energized and agitated that they constantly collide with each other. In the early universe, temperatures were so extreme that matter did not exist in the way we know it today. Instead of atoms, there was a hot, dense plasma composed of quarks and gluons, the building blocks of matter. This cosmic soup of particles, although it did not generate audible sound as we know it, was a place full of vibrant activity. Now let's think about how sound is produced. We need a medium, something that transmits those sound waves. On Earth, sound travels through air, water, or even solids. But in the early universe, the situation was very different. The dense fog of hot particles could not allow sound to travel as it does in our everyday world. So what was happening? Although there was enough energy to create vibrations, the type of sound we might hear was completely different from what we experience on Earth. As the universe began to expand, conditions started to change. The temperature began to drop. But how does this affect sound production? Imagine you are in a closed, hot space. As it cools down, particles start to move more slowly, eventually allowing matter to form. This cooling process was crucial as it allowed protons and electrons to combine to form atoms. However, before this, vibrations were trapped in the hot plasma, and the sound we could imagine remained inaudible. At this point, it becomes clear that the temperature of the early universe not only played a role in the formation of matter, but also in creating an environment where sound, as we understand it, could not exist. As the temperature continued to decrease, the universe slowly cooled, allowing light to begin to emerge, but sound was still in the air, or rather, in the absence of it. The era of recombination was a fundamental moment in this process. During this period, approximately 368,000 years after the Big Bang, electrons and protons finally combined to form atoms. It was as if the universe was finally releasing a warm sigh after being in a tumultuous state of effervescence. At this moment, matter and radiation decoupled, meaning light could finally travel freely through space. But what happened to sound? The answer is that there was no suitable medium for sound waves to propagate. Still, not everything was lost. In the chaos of primordial plasma, acoustic waves were generated as the universe expanded and cooled. These waves were vibrations in the plasma, and although we could not hear them, they did have an impact on how the universe was structured. These sound waves, although inaudible, were crucial in the formation of the first galactic structures such as the galaxies and galaxy clusters we see today. It's a fascinating concept. The silence of the Big Bang was, in a way, the precursor to the cosmic symphony. As the universe continued to expand, conditions became more favorable for the formation of stable structures. But sound itself, in its purest form, remained an impossible phenomenon in the vast emptiness of space. So how can we connect this with what we know about our own perception of sound? The reality is that our understanding of sound is deeply rooted in our experience on Earth, where air and other media allow sound waves to propagate. However, in the cosmos, the void is an overwhelming silence. The temperature of the early universe was a key player in this cosmic drama. Without it, the necessary conditions for matter to form would not exist, and therefore we could not have had the universe as we know it today. So every time we look at the starry sky, let us remember that the silence we perceive is a reflection of a time when temperature and energy played a crucial role in the creation of everything we see. In summary, the temperature of the universe in its early moments not only influenced the creation of matter, but also defined the nature of sound in the cosmos. The absence of a suitable medium combined with extreme conditions created an environment where sound, as we know it, could not exist. The Big Bang was, in fact, a silent event, but in its silence it set the stage for the wonder of the universe. In the vast and mysterious universe, there is a crucial moment that marks the beginning of everything we know, and that is the moment of recombination. But what does this really mean? The era of recombination refers to a specific period, approximately 370,000 years after the Big Bang, when the universe underwent a radical change. It is at this instant that matter and radiation began to separate in a way that would affect everything that came afterward. Can you imagine a universe where light and matter finally shake hands? To understand the importance of this period, it is essential to remember that, before recombination, the universe was an extremely hot and dense place. Like a boiling soup, it was filled with charged particles and energy that prevented light from traveling. Everything was so agitated that light could not escape. In this primitive universe, radiation and matter were in a state of chaos, where photons, which are particles of light, constantly collided with electrons and protons. How could something as luminous as light remain trapped in a storm of particles? Recombination marked a moment of calm. As the universe expanded and cooled, conditions changed. Electrons began to combine with protons to form hydrogen atoms, and finally, light could travel freely. But what does this imply for sound? At this point, the question becomes intriguing. If sound depends on the vibration of particles in a medium, what happens when matter and radiation separate? During the era of recombination, the universe began to become a quieter place. However, it is crucial to highlight that before this period, sound as we know it was completely impossible. Why? Because sound needs a medium to propagate, like air, water, or even a solid. But in that primitive universe, the density and temperature were so extreme that any attempt to produce sound would have been lost in the clamor of colliding particles. So in reality, there was no silence in the sense we understand, but rather a chaos of vibrations and energy. As the universe expanded, the temperature continued to decrease, allowing matter to organize into more stable structures. It's as if a group of musicians on a stage, who were previously playing all at once and in a disorganized manner, began to follow the same rhythm and play together harmoniously. But curiously, in this process, sound as we know it was not present. Is it possible that at the most significant moment of the creation of the universe, the Big Bang, sound simply did not exist? Indeed, the era of recombination shows us that, although matter and radiation separated, there was no suitable medium for sound to propagate. Instead of melodies, what remained was an echo of what could have been. However, before you feel disheartened by the absence of sound, think about how the universe As it cooled and expanded, laid the foundations for everything that would come afterward: galaxies, stars, planets, and of course, life itself. Still, the absence of sound does not mean that nothing occurred. At that moment, acoustic waves were generated within the primordial plasma, which were vibrations that, although they could not be heard, carried crucial information about the structure of the universe. These waves resemble the ripples in a pond that form when you throw a stone. Although you cannot hear the movement of the water, you can see how they propagate. But here, on this cosmic scale, those waves were not audible, and only left traces in the background radiation that reaches us today. The cosmic microwave background radiation, which is the light we can still observe today, is a remnant of those early moments. It tells us the story of the era of recombination, like an ancient melody that has been distorted over time. But what does this mean for us? How do these events influence our understanding of the universe? The era of recombination is, in fact, a fascinating chapter in the history of the cosmos. It reveals to us that silence is not simply the absence of sound, but a space filled with potential. Without that primordial silence, matter would not have had the opportunity to organize itself, to form structures that would eventually give rise to stars and planets. It is a reminder that even in stillness, the foundations of life itself can be found. As we reflect on the era of recombination, it is important to consider how this period has influenced our perception of the universe. In a world where sound is an integral part of our experience, it is fascinating to think that at the beginning of everything, the music of the cosmos was in a deep silence, and so the story of the universe continues, not only as a tale of explosions and chaos, but also as a symphony of silence that invites us to keep exploring the mysteries that still remain to be discovered. The vast primitive universe just after the Big Bang was a place of chaos and energy. In this sea of particles and radiation, acoustic waves emerged amidst the dense soup of plasma that filled the cosmos. But what are these waves, and why are they relevant to our understanding of the universe? Sound waves are vibrations that travel through a medium such as air or water. On our planet, we hear them when someone speaks, when music plays, or when thunder rumbles in the sky. However, in the early universe, the conditions were drastically different. What would happen if we could hear the sound of the Big Bang? The answer is complex, as those waves, while present, do not translate into what we understand as audible sound. As the universe expanded, acoustic waves formed in the primordial plasma, a state of matter so hot and dense that electrons and protons were in constant turmoil. Imagine an ocean of energy where the waves are not of water but of vibrating particles. These vibrations propagated through that plasma, generating patterns that could have been interpreted as sound in a very abstract sense. But why can't we hear those waves? The main reason lies in the fact that space, for the most part, is a vacuum. In the vacuum of space, there is no medium through which those acoustic waves can travel. Think of a balloon that you blow air into. If you vibrate the balloon, the sound will travel through the air and you will be able to hear it. However, if you tried to do the same in space, the sound would dissipate, as there is no air to carry those vibrations. So although those waves were generated in the early universe, they never translated into sound that we could perceive. But why study these waves then? The answer is that they provide valuable information about the conditions of the universe in its early moments. By analyzing the traces these waves left in the cosmic microwave background radiation, scientists can infer details about the density, temperature, and composition of the primordial universe. It's like examining the ripples on the surface of a lake after throwing in a stone. Each wave tells a story about what happened below. One fascinating aspect is that although we cannot hear these waves, we can study them through their effects. For example, fluctuations in the cosmic microwave background radiation show us the distribution of matter in the universe and how it clusters to form galaxies and other structures. It could be said that these waves are like the fingerprints of the universe, revealing secrets about its origin and evolution. The era of primordial plasma was crucial for the formation of these waves. At that time, matter and radiation were so intertwined that any attempt to separate them resulted in a tumultuous dance of energy. But when the universe began to expand and cool, there came a moment when matter and radiation decoupled. This period, known as the era of recombination, was fundamental to the history of sound in the universe. At this point, the plasma turned into neutral atoms, allowing light to begin traveling freely. However, the acoustic waves had already played their role, leaving a mark on the structure of the cosmos. The acoustic waves of primordial plasma are not sound in the sense we know, but they are an important clue about how the universe was organized. They are like echoes of a symphony that was played billions of years ago, whose chords still resonate in the cosmic microwave background radiation. Thus, every time scientists study this radiation, they are figuratively listening to a melody from the past. The nature of these waves also leads us to reflect on the relationship between sound and light. Although they are distinct phenomena, both provide us with information about the universe. Sound waves require a medium to propagate, while electromagnetic waves, like light, can travel through a vacuum. This duality reminds us that the cosmos has multiple ways of communicating with us, and that our human senses are just a small part of the story. The study of sound waves in the early universe is a constantly evolving field. As we develop new technologies and observation methods, new possibilities open up to better understand these primordial vibrations. Each discovery brings us closer to unraveling the secrets of the universe and, in doing so, invites us to question our own existence and our place in the cosmos. With each step we take in our quest for knowledge, we encounter profound questions about the nature of reality. What does it mean that the universe began in absolute silence? How does this affect us in our search for meaning? The answers to these questions may not be easy, but they are fundamental to our understanding of existence itself. At the end of the day, the study of acoustic waves in the early universe is not only a scientific exploration, but also a philosophical reflection. It reminds us that although the cosmos may have begun in silence, each discovery we make is a new chord in the grand symphony of the universe. And so, as we continue to listen and learn, we can appreciate the beauty of the silence that gave rise to all that we know. What is cosmic background radiation, and why is it so important for understanding the Big Bang? Often, when we think of the echoes of the universe, we imagine sounds traveling through space. However, the Big Bang was a silent event, and its auditory legacy manifests in a very different way, through cosmic background radiation. Let's think of this radiation as a kind of echo of the Big Bang, but instead of being a sound wave, it is an electromagnetic wave. This means we do not hear it with our ears, but we detect it through scientific instruments. This radiation is like a photograph of the early moments of the universe, capturing the essence of its birth. But how was this phenomenon discovered? The discovery of cosmic background radiation dates back to 1965, when two scientists, Arno Penzias and Robert Wilson, were conducting experiments with a radio telescope. Unintentionally, they stumbled upon a persistent signal that filled the sky. It was not interference or background noise, but a uniform radiation coming from all directions. This finding was crucial because it provided tangible evidence for the Big Bang theory. This cosmic echo has a temperature of about 2.7 degrees Kelvin, which is extremely cold. But how can something so cold be related to the heat of the Big Bang? The key lies in the expansion of the universe. When the Big Bang occurred, the universe was a hot and dense soup. As it expanded, it cooled, and that energy was distributed in the form of radiation. So what we perceive today as cosmic background radiation is, in fact, a remnant of that primordial heat. Cosmic background radiation is not evenly distributed in space. Instead, it presents slight variations in its temperature, which are fundamental for understanding how galaxies and other structures in the universe formed. Each small change in this radiation tells us a story about the formation of the cosmos. Isn't it fascinating to think that by observing this radiation, we are looking back in time almost to the very moment of the Big Bang? Now imagine that cosmic background radiation is like a painting in which each brushstroke represents a part of the history of the universe. These variations reveal the original distribution of matter and energy in the early universe. Without these details, it would be very difficult to understand how we transitioned from a singular hot point to a vast universe filled with stars and galaxies. The study of this radiation has also led to surprising discoveries. For example, from its analysis, scientists have been able to estimate the age of the universe, which is calculated to be approximately 13.8 billion years. Imagining that so much time has passed since that initial moment is truly astonishing. But what about the implications of an expanding universe? Cosmic background radiation also provides clues about the nature of dark matter and dark energy, two of the great mysteries that still elude us. These components are fundamental to understanding how the universe behaves, and cosmic background radiation acts as a map that helps us navigate these mysteries. However, what does all this mean for our daily existence? When we look at the night sky and see the stars, we are witnessing a universe that has changed drastically since the Big Bang. Cosmic background radiation reminds us that although the universe seems like a quiet and serene place, it is full of history and movement. Each star is a beacon connecting us to this past, and the radiation offers us a window into that primordial time. The study of this radiation is not only relevant for astrophysicists, but also raises profound philosophical questions about our place in the cosmos. What does it mean to be part of a universe that began in such an extreme state and has evolved in such a complex way? The presence of cosmic background radiation resonates with the idea that we are all, in some way, part of this vast story. So as we delve into the mystery of the cosmos, cosmic background radiation becomes our guide. It helps us understand the extreme conditions that existed just after the Big Bang and gives us insight into how the universe has come to be what it is today. Isn't it incredible to think that although the Big Bang was silent, its legacy speaks to us through this radiation? Each discovery related to cosmic background radiation is another step toward understanding who we are and how we fit into the grand scheme of the universe. And as we continue to explore, we can expect that each answer will lead us to new questions, keeping our curiosity about the cosmos alive. The pursuit of knowledge never stops, and cosmic background radiation is just one of the many keys that will help us unravel the secrets of the universe. The vastness of the universe is filled with mysteries, and one of the most intriguing is how sound behaves during cataclysmic events. Have you ever wondered what happens to sound when massive explosions occur in space? In an environment where vacuum is the norm, the idea of sound becomes a fascinating enigma that deserves our attention. To understand this, it is essential to remember that sound is a vibration that travels through mediums, such as air, water, or even solids. But in space, where there is no air to act as a vehicle for these vibrations, sound cannot propagate. So in a sense, we could say that space is an absolute silence compared to our usual environment on Earth. However, that does not mean there is no activity. Cataclysmic events such as supernova explosions are true orchestras of energy, but silence prevails. Imagine the explosion of a star. In our world, it would be a sound spectacle, but in space, that same explosion becomes an impressive visual phenomenon with shockwaves and bright light, while sound simply has no way to reach our ears. So what happens to the vibrations generated by these events? Although we cannot hear them, these vibrations can be detected in other ways. The shock waves from a supernova, for example, are similar to the sound waves we know, but they travel through other mediums, such as plasma or interstellar gas. The energy released in a stellar explosion disperses through those materials, creating wave patterns that, although not sound in the classical sense, represent a form of cosmic sound. Scientists can study these waves to learn more about the nature and behavior of stars. Now, what about the Big Bang? This cataclysmic event took place in an environment that was extremely dense and hot, which means that in its early moments there would have been a kind of sound in the form of vibrations through particles. However, as the universe expanded and cooled, sound as we know it faded away. But does this mean there was no music in the primitive universe? Not exactly. Although we could not hear those vibrations, acoustic waves were generated in the primordial plasma. Imagine the sound of a bell gradually fading away. At first, it sounds loud and clear, but as it moves away, its sound becomes fainter. The same happens with acoustic waves in the early universe. As space expanded, those vibrations dissipated, transforming into what we now know as cosmic background radiation. This phenomenon is like the echo of a great concert moving away, leaving behind a trace of what once was. In the context of cataclysmic events, we can think of other explosions in the universe, such as those occurring in the cores of active galaxies. These explosions are so powerful that they generate shock waves that can travel great distances in space, but again, sound does not reach our ears. However, astronomers can detect the electromagnetic radiations emanating from these events, giving us clues about their nature. The comparison between the silence of the Big Bang and other cosmic events is fascinating. On our planet, an explosion can be both a visual and auditory spectacle. But in space, the experience is completely different. The universe is a place where energy and matter interact in ways that challenge our understanding. Supernova explosions not only light up the sky, but also tell us stories about the creation of heavy elements and the dynamics of the cosmos. It is curious to think that although sound seems essential to our human experience, the universe continues to function without it. In the vastness of space, silence becomes a canvas on which cosmic stories are drawn. The absence of sound is not a void, but a reminder of the complexity of the physics that governs our universe. So, how does all this relate to our perception of sound? Humans, being auditory beings, often interpret the world through what we hear. However, the universe teaches us that there is much more than we can perceive with our senses. The science behind these cataclysmic events invites us to expand our understanding and accept that there are dimensions of reality that remain beyond our reach. Acoustics in space is a constantly evolving field. As technology advances, scientists are developing new ways to study the vibrations and waves that, although invisible and silent, have a significant impact on the structure of the cosmos. These studies allow us to glimpse a universe full of activity, even when silence seems to reign. Finally, when thinking about the silence of the Big Bang and other cataclysmic events, we realize that the universe has its own language, one that goes beyond sound. Energy, light, and vibrations are the notes of this cosmic symphony, one that continues to resonate through time and space, reminding us that despite its silence, the cosmos is alive and constantly changing. The human perception of sound is a fascinating phenomenon that not only connects us with the world around us, but also helps us understand deeper aspects of the universe. Have you ever wondered how it is possible for a sound to evoke emotions, memories, or even images in our minds? The answer lies in the complexity of our auditory system and the way our brain processes sound waves. Sound, in its essence, is a vibration that travels through a medium, whether it be air, water, or even solids, until it reaches our ears. But what exactly happens when we listen? When the vibrations reach the eardrum, it moves and transmits that information to a series of structures in the inner ear. From there, nerve signals send the information to the brain, where it is interpreted and converted into what we know as sound. But why is this process so important? Because it allows us to interact with our environment, communicate and experience life in a unique way. From the song of a bird to the music we listen to, every sound we perceive has a story behind it. However, there is a world far beyond our everyday experience. While the sounds around us are part of our reality, the universe has its own symphony that we cannot always hear. Imagine a vast ocean of space where sound waves cannot travel. This raises an intriguing question. How can a universe that began in silence influence our perception of sound? Consider the fact that humans, for the most part, are designed to hear within a specific range of frequencies. Our hearing has adapted to the needs of life on Earth, where air acts as a medium for sound transmission. In the vacuum of space, where there is no air or any other medium, sound becomes an abstract concept. But what about the sounds that might have existed in the primordial universe? Although we cannot hear them, scientists have theorized that there could have been acoustic waves in the hot plasma that existed after the Big Bang. Isn't it amazing to think that even though we are unable to hear them, those waves could have carried crucial information about the formation of the universe? The way we perceive sound is also related to the evolutionary history of our species. Our ancestors relied on sound for survival. Hearing the crack of a branch indicating the presence of a predator, or the call of a mate in the distance. In this context, hearing became a vital tool. As humanity has progressed, our ability to create and appreciate complex sounds, such as music, has evolved in fascinating ways. But what is the impact of this evolution on our understanding of the cosmos? Music, often considered one of the purest forms of human expression, also has its own place in the exploration of sound in space. There are scientists who have turned data from the universe into music, creating an art form that is not only beautiful but also connects us to the cosmos in a very intimate way. Wouldn't it be incredible to hear a composition that represents cosmic events, such as the collision of galaxies or the birth of a star? The perception of sound also leads us to reflect on the nature of silence. In a universe that began in absolute silence, sound as we know it is a relatively recent phenomenon in cosmic time. This primordial silence raises philosophical questions about our existence and our place in the cosmos. If the universe began in silence, what does this mean for us as beings that depend on sound to communicate and connect? Sound waves can be seen as a metaphor for human connection. Every time we speak or listen, we are participating in an exchange that goes beyond words. This exchange can be considered an echo of the universe itself, where the vibrations of our being resonate in a broader context. How does this relate to the vibrations in the cosmos, which, although inaudible, remain part of our reality? The science behind acoustics in space is equally fascinating. Researchers have developed technologies to capture and analyze vibrations and sound waves in places like outer space. Although we cannot hear those sounds in the same way we do on Earth, studying them allows us to gain a clearer insight into cosmic processes. What discoveries await us in the future as our understanding of spatial acoustics expands? Ultimately, the human perception of sound is a reminder of our connection to the universe. Through music, communication, and science, we seek to understand and make sense of what surrounds us. Thus, even in a universe that began in silence, sound manifests in surprising and meaningful ways. Every note, every vibration, every whisper of the cosmos invites us to explore beyond what we see and to listen to the symphony that surrounds us. In this journey, the silence of the Big Bang becomes a gateway to the vast and wonderful reality of the universe. Have you ever wondered how scientists study sound in the vast universe? The answer to this intriguing question may seem complicated, but in reality, it is a fascinating field that blends physics, acoustics, and cosmology. To understand it, we must first remember that sound is a vibration that travels through a medium such as air, water, or even solids. But what happens when we find ourselves in space where there is no air or water? This is where the study of sound becomes truly interesting. Scientists have developed innovative methods to understand how sound works in the cosmos. Imagine you are in a huge ocean without water, just emptiness. In this environment, sound could not travel as it does on Earth. However, that doesn't mean scientists are sitting idly by. They use tools like computer simulations and mathematical models to explore how sound waves might behave under different conditions in space. Acoustics in space is not just a curiosity, it has important implications for our understanding of the universe. By studying how sound waves behave in extreme environments, scientists can gain insights into cosmic events, such as supernova explosions or galaxy collisions. But how do they manage to capture something they cannot hear? One of the key strategies is converting sound waves into electromagnetic waves which can be detected. Think of it as trying to listen to a whisper through a wall. Instead of trying to hear the sound directly, you might place a microphone on the opposite side and record what is transmitted through the wall. In space, scientists do something similar, using telescopes and highly sensitive detectors. Moreover, satellite technology plays a fundamental role in this process. Scientists send probes into space that can measure different phenomena and send data back to Earth. These probes not only collect light and radiation, but can also measure variations in pressure that, although not audible sound, provide vital information about conditions in space. A fascinating example of this is how astronomers have detected pressure waves generated by star explosions. Although we cannot hear these explosions in the vacuum of space, the data collected allows us to understand the events that caused them. This is similar to how a sheet of paper can vibrate when someone speaks nearby. Even though we cannot hear the words, we can see the effect they have. Computer simulations are another crucial tool in researching sound in space. Scientists create models that simulate how sound waves interact with different types of matter and energy. Imagine a video game where you can adjust the environmental conditions to see how the outcomes change. This is how researchers can predict how sound waves would behave in the early universe or in extreme situations. In the modern era, advances in technology have allowed scientists to visually display what they could previously only describe. By converting sound waves into graphics that we can see, they offer us a unique perspective on phenomena that would otherwise be beyond our reach. This not only makes science more accessible, but also sparks our curiosity about what lies beyond our planet. Despite these advances, there are significant challenges. The nature of sound and how it manifests in space remains a mystery in many respects. For example, the connection between sound and dark matter is an active area of research. Dark matter cannot be seen or detected directly, but its influence on the universe is undeniable. Could sound play a role in how it interacts with visible matter? This is an open question that many scientists are eager to explore. Acoustics in space also reminds us of the fragility of our perception. On Earth, sound is a fundamental part of our daily experience. But in the vast silence of space, we face the reality that there is much more in the universe than we can perceive. This leads us to reflect on our own existence and our place in the cosmos. As we continue to explore the universe, we are likely to discover new ways to understand sound and its relationship with other cosmic phenomena. Researching how sound propagates in space may not only reveal secrets about the universe's past, but also open new doors for the future of space exploration. In conclusion, the study of sound in the cosmos is an exciting field that challenges our notions of what it means to hear and understand. Although space may be a silent place, scientists have found ingenious ways to translate what we cannot hear into knowledge that brings us closer to understanding the universe we inhabit. So the next time you think about sound, remember that there is much more at stake, even in the silence of space. Did you know that sound and light, although both are waves, are fundamentally different in their nature? While sound is a vibration that travels through a medium, whether air, water, or solids, light travels in the vacuum of space as an electromagnetic wave. This difference is key to understanding why, despite the Big Bang being a monumental event, it produced no sound that we could hear. Think about how we listen to music. When a musician plays a guitar, the strings vibrate, and these vibrations are transmitted through the air, reaching our ears. However, if you tried to play a guitar in space, you wouldn't hear anything. This is because there is no air in the vacuum of space to carry those vibrations. Thus, the Big Bang, although it was an explosion of energy and matter, occurred in a void that could not transmit sound. Now, why is this difference between sound and light so interesting? Light allows us to observe the universe, while sound connects us to experiences closer to our daily lives. Imagine looking at a star that is millions of light years away. The light you see now has traveled for an incredible amount of time, revealing information about that star. But if you could hear it, you would realize that there would be no sound accompanying that light, as there is no medium for it to travel through. Let's talk about waves. Sound waves and electromagnetic waves are two types of waves that carry information. Sound waves require a physical medium to propagate, while light waves do not depend on anything. This means that, although the universe is filled with electromagnetic radiation, sound is restricted to places where there is a suitable medium. In the case of the Big Bang, the expansion of the universe created a vacuum where sound could not exist. Imagine you are at an outdoor concert. If there is wind, the music might reach you differently. But if you were in space, even the best concert would be absolute silence. The light from distant stars and galaxies offers us a visual symphony, but the silence of space reminds us that not everything happening in the universe can be heard. What about human perception? Our ears are designed to pick up vibrations in the air. When we hear a sound, our brain translates it into experiences and emotions. The ability to hear connects us to our environment. However, in space, where there is no medium for those vibrations to travel, our perception of sound stops. This leads us to question how we interpret the vastness of the cosmos. You might wonder, how are sound and light related in science? Light provides us with a way to study the universe, while sound, in its absence, gives us an idea of what we cannot hear. Light waves allow us to observe the Big Bang through cosmic background radiation, a kind of echo of the event that occurred billions of years ago. However, this echo is not sound but an electromagnetic signal that gives us information about the early moments of the universe. The science of acoustics in space also shows us how fascinating it is to explore these differences. Scientists have developed methods to study acoustic properties in different environments, even in conditions that simulate the vacuum of space. These experiments help us understand how sound might behave on other planets or in extreme situations, although always with the limitation that it cannot propagate in a vacuum. The relationship between sound and light also leads us to reflect on how we interact with the universe. Light may be the way we see and understand our cosmic environment, while sound, which we cannot capture in space, reminds us of the limitations of our perception. Science advances, and as we develop new technologies, we find ways to explore the universe beyond our sensory capabilities. So, what does this mean for our understanding of the Big Bang? It means that although that moment was the beginning of everything we know, it was a silent event. And in that silence lies a profound lesson about the nature of the universe. It teaches us that there are many aspects of reality that we cannot perceive directly, but that we can still understand through science. Finally, the difference between sound and light is not just a topic of physics, but a reflection on our existence. It invites us to explore beyond what we hear and see, to question our assumptions, and to seek answers in the mysteries of the cosmos. The next time you look at the starry sky, remember that the silence surrounding it is part of the beauty of the universe and its history. The Big Bang is undoubtedly one of the most fascinating and extraordinary events in our universe, but it is often misunderstood. What exactly happens in people's minds when they hear about this phenomenon? Many times, misconceptions arise that can lead to confusion. Let's demystify some of those misconceptions and clarify the science behind them. First, let's talk about sound. Some people imagine that the Big Bang was like a loud explosion, like a burst of fireworks in the sky. However, sound as we know it does not occur in a vacuum, and space is mostly a vacuum. Therefore, an event as monumental as the Big Bang could not have emitted an audible sound, as there was no air or other medium to carry it. If you had been there at that moment, all you would have felt would be the vibration of time and space expanding. But what about the idea that sound waves could have existed in some form? It is true that the early universe was filled with plasma, a state of matter in which atoms are broken down into electrons and nuclei. In this environment, acoustic waves could have been generated, but these would not be the sounds we hear today. Instead of pleasant melodies, they would be fluctuations in the density of matter, something that neither our ears nor our brains could interpret as sound. A common confusion also lies in how the Big Bang relates to the creation of structures in the universe. Some people think that sound could have influenced the formation of galaxies or star systems. However, it is crucial to remember that sound requires a physical medium to travel. In the vacuum of space, There is nothing to propagate those waves, so even if acoustic waves existed in the primordial plasma, their influence dissipates quickly in the vastness of the cosmos. Now let's talk about the concept of silence. Some people are puzzled to hear that the universe began in silence. Isn't it strange to think that such a monumental event had no sound? This silence invites us to reflect on our understanding of what it means to begin. The silence of the Big Bang is not just an absence of noise, it is the premise of a universe unfolding, expanding, and eventually giving rise to everything we know today. It is a silence that is, in itself, a powerful statement about the nature of the cosmos. Another misconception that circulates is that if there was no sound, then there was no activity. But this is where physics comes into play. Although there was no sound per se, there was immense activity. The first moments of the universe were filled with energy and transformation. Matter was forming and the conditions were extreme. The lack of sound does not imply inaction, but rather a primordial chaos that preceded the creation of stars and galaxies. Then there is the myth that the Big Bang was a point in space that exploded. This is an idea that has been very popular in culture, but it is essential to understand that the Big Bang did not occur in a specific location within space. Instead, it was the expansion of space itself. Incredible, right? It's not just that the universe is expanding, but that every point in the universe is moving away from the others. Therefore, there is no center from which everything expands, further complicating the notion of sound. Some people also believe that sound could have been heard on Earth at some point. But how could that be possible if the Earth did not exist at that time? The formation of our planet took place billions of years after the Big Bang. What we hear today are echoes of events that have happened in time and space. But those echoes are not the sound of the Big Bang itself. Rather, they are the music of the evolving universe. The absence of sound in the Big Bang also raises philosophical questions. If the universe began in silence, what does this mean for us, human beings living in a world full of sounds? Does this represent some kind of void in our understanding of existence? This primordial silence may serve as a reminder that the cosmos has its own rhythms and melodies that go beyond what we perceive with our senses. It is also important to mention that, although the Big Bang was silent, there are other phenomena in the universe that emit sounds. For example, stars emit vibrations that, when translated into audible frequencies, become cosmic music. But those melodies are the result of stellar evolution, not of the initial explosion of the universe. Science is constantly working to unravel these mysteries. Scientists strive to better understand how sound waves are formed in different environments. And although they cannot hear the Big Bang, they study other cosmic events that give us clues about the nature of sound in the universe. Each discovery brings us one step closer to demystifying what really happened in those early moments. The silence of the Big Bang should not be seen as a meaningless void, but as a space full of potential. In the silence lies the promise of creation, an expanding universe where stars will eventually emerge, and with them, the sound of the cosmos. So the next time you hear about the Big Bang, remember that this silence is actually the beginning of everything we know and the foundation of our quest to understand the universe. What really happens in the silence of the Big Bang? For many, this question may seem strange, as we are used to associating sound with explosive and vibrant events. However, when astrophysicists reflect on the origin of the universe, the absence of sound becomes a fascinating topic. To delve into this mystery, let's listen to some experts in the field. The first scientist we interviewed is Dr. Javier Morales, an astrophysicist who has dedicated his career to studying the cosmos. He explains that at the moment of the Big Bang, the universe was an extremely hot and dense place. But as it began to expand, the matter cooled and dispersed. The curious thing, says Dr. Morales, is that in that primitive state, although there were many particles moving, there was no medium through which sound could travel. This leads us to ponder, how can it be that in such a monumental event there was no sound? The answer to this question takes us to the very nature of sound. Dr. Ana Garcia, an expert in acoustics, enlightens us on how sound is produced in our daily lives. Sound is a vibration that travels through a medium, whether it be air, water, or even solids. Without a medium, it simply cannot travel. So when we think of the Big Bang, we must remember that the vacuum of space does not allow those vibrations to propagate. It's like trying to listen to music underwater, says Dr. Garcia. Even if the music is playing, it's very hard to hear it if the water doesn't carry it properly. Another interesting point that Dr. Morales mentions is the era of recombination, a crucial moment in the history of the universe. It was when matter and radiation decoupled, he explains. This means that before this event, the universe was like a dense broth where particles were stuck together. But when they separated, a vacuum was created that prevented the propagation of sound. Imagining it is like thinking of a group of friends who are so close that they cannot move. When they finally separate, the noise they made disappears. Still, Dr. Morales reminds us that this does not mean there was no activity. In the early universe, there were acoustic waves vibrating in the primordial plasma, he says. They were like echoes of what had occurred, even though they did not translate into sounds we could hear. This idea that sound waves existed in a primordial state but were not audible is intriguing. It makes us think about how often many things happen without us being aware of them. Dr. Garcia offers another perspective by mentioning cosmic background radiation. This is the echo of the Big Bang, but it is not sound, she clarifies. It is electromagnetic radiation that tells us about those early moments of the universe. Its discovery was a milestone that changed our understanding of the cosmos. It is a reminder that there is much more in the universe than what our senses can capture. At this point, a fascinating question arises. How does sound behave in other cosmic events? Dr. Morales points out that although the Big Bang was silent, other phenomena such as supernovae generate sound waves. In those cases, sound behaves in surprising ways. In a vacuum, it cannot be heard, but in dense media, like the gas in which a star explodes, sound can travel, he explains. This invites us to think about the vastness of the universe and how different conditions can modify our perceptions. Moreover, we cannot forget the human perception of sound. Dr. Garcia reminds us that we are beings who depend on our senses to make sense of the world. Sound has been fundamental to our evolution, but it is also a reminder that what we do not hear is also important. She says, the absence of sound in the Big Bang invites reflection on how we interpret our existence in the cosmos and the relationship we maintain with our surroundings. The science of acoustics in space is a field that has captured the attention of many researchers. Scientists have developed simulations to study how sound waves would behave under different conditions in the universe, says Dr. Morales. It is an intriguing area that continues to evolve. This makes us wonder what discoveries the future holds for our understanding of sound and space. Finally, Dr. Garcia shares a provocative thought. Sometimes silence can be as powerful as sound. The fact that the Big Bang was a silent event teaches us that there are aspects of the universe that we still do not fully understand. Reflecting on this can be challenging, but it is also an invitation to continue exploring, investigating, and questioning. The absence of sound in the Big Bang is not just a scientific fact. It is a reminder that the universe is a place full of mysteries that are still waiting to be revealed. The next time we look at the stars, perhaps we will remember that, at its origin, everything began in a deep silence, a silence that invites us to listen to the stories that have yet to be told in the vast cosmos. Since the moment the Big Bang took place, the universe has been in constant evolution. But how has it changed since then? As time progresses, the events and conditions that once defined the cosmos transform, shaping what we know as the current universe. In this journey through time, it is fascinating to observe how each moment has left its mark on the structure and acoustics of the cosmos. The expansion of the universe is one of the most intriguing phenomena. Imagine a balloon being inflated. As air is introduced into the balloon, the surfaces separate. The universe works in a similar way. Since the Big Bang, it has been expanding, which has influenced how galaxies are distributed and how large-scale structures form. But what does this mean for sound? As the universe expands, the sound waves that might have been generated in its early stages are affected. Space becomes increasingly vast and conditions change rapidly. The extreme temperatures of the primitive universe also played a crucial role. In the first moments after the Big Bang, the heat was so intense that matter existed in the form of a dense plasma. In this state, subatomic particles collided with each other at high speeds. However, as the universe expanded and cooled, conditions changed. What happened then? Matter began to clump together and form more complex structures. But sound as we know it could not manifest due to the lack of an adequate medium in the vacuum of space. The era of recombination was a critical period in the development of the universe. At this moment, electrons and protons combined to form hydrogen atoms, and the radiation that had been trapped began to be released. But what impact did this have on the acoustics of the universe? With the release of radiation, sound as a physical phenomenon became even more complicated. The sound waves that might have existed in the primordial plasma did not translate into audible sounds. Instead, they became pressure waves that dispersed through space, leaving a silent echo in the vastness of the cosmos. Acoustic waves in the early universe are a fascinating topic. Although we cannot hear those sounds, we know they existed. Fluctuations in the density of the primordial plasma created waves that traveled through the universe. However, these waves were not sound waves in the traditional sense, as they required a medium to propagate. Thus, the universe, in its earliest phases, was full of activity but in a deep silence. The cosmic background radiation is one of the most important remnants of the Big Bang. This echo of the past which fills the universe is like a fingerprint of the events that occurred billions of years ago. But what relation does it have to sound? Although we cannot hear the whisper of the Big Bang, this radiation provides us with clues about what happened in those initial moments. It is a reminder that the universe, although silent, is full of history. Cataclysmic events in the cosmos also teach us about sound. Imagine a supernova, a stellar explosion that releases energy in unimaginable amounts. On Earth, we would hear the roar of an explosion, but in space, sound is drowned in the vacuum. This leads us to wonder, how do we perceive sound if the universe is filled with these violent events? The answer lies in our own existence. Our senses are designed to capture vibrations in a medium. Like air and in the cosmos, that medium is scarce. The human perception of sound is a marvel in itself. Our ears are sensitive to a wide range of frequencies, allowing us to enjoy music, voices, and the sounds of nature. But what does this mean in the context of the universe? Hearing connects us with our environment, but it also invites us to reflect on what the universe might have been like in its infancy. The lack of sound at the Big Bang is not just a physical fact, but it also makes us question our relationship with the cosmos. The science of acoustics in space has become a fascinating field of study. Scientists have developed experiments and simulations to better understand how sound waves behave in space. Through this research, they have been able to gain a clearer insight into how sound might act under different conditions in the universe. What future discoveries could change our understanding of sound and space? Only time will tell. Sound and light, although different in nature, are complementary in our exploration of the cosmos. While sound waves require a medium to travel, electromagnetic waves can move through the vacuum of space. This leads us to wonder, how can we use both phenomena to gain a more complete picture of the universe? The answer lies at the intersection of acoustics and astronomy, where both fields converge to unveil the secrets of the cosmos. Throughout history, myths and misunderstandings about the Big Bang and sound have arisen. It is often mistakenly thought that there was a great roar at the beginning of the universe. However, clarifying these misconceptions is essential for understanding the science behind them. The silence of the Big Bang is not an obstacle, but an opportunity to explore the wonders of the cosmos from a new perspective. The testimonies of scientists who have dedicated their lives to studying the universe are an invaluable resource. Their perspectives on the absence of sound in the Big Bang and its importance in cosmology enrich our understanding. Listening to their voices reminds us that despite the silence, the universe is full of activity, history, and mystery. Finally, reflecting on the evolution of the universe invites us to consider how our perception of sound and life itself has changed. From the earliest moments to the vast expansion today, each change has left an indelible mark on how we experience the cosmos. What does the future hold for us? We can only imagine the wonders yet to be discovered as we continue to explore the silence that surrounded the birth of everything. The silence of the Big Bang, then, is not just a historical fact, but an invitation to reflect on our existence in a universe that, despite its immensity and complexity, remains a mystery to be unveiled. In this journey through the cosmos, each discovery brings us one step closer to understanding not only the universe we inhabit, but also our place within it. The silence surrounding the Big Bang poses a fascinating question. What does it really mean for us that the origin of the universe was a soundless event? For many, the idea of a cosmos beginning in absolute silence may seem strange, even unsettling. But what if that silence has deeper implications about our existence and the nature of reality? Let's consider for a moment how the absence of sound in the Big Bang invites us to reflect on the nature of the universe. In a world where sound is an integral part of our lives, from the laughter of a child to the song of a bird, the silence at the beginning of the cosmos leads us to question what other aspects of our experience might be equally deceptive. Is it possible that the universe in its essence is a place of profound silence, beyond what our senses can grasp? Science has discovered that the universe is not only vast and expanding, but also incredibly ancient. However, this ancient cosmos began in a state of absolute calm. This idea may be difficult to accept, as we are accustomed to associating great events with thunderous noises. But what if that initial silence is a manifestation of an even more astonishing reality? A universe that, before being filled with stars and planets, existed in a state of pure potentiality. The silence of the Big Bang also reminds us that what we perceive is only a fraction of reality, just as a fish in water is unaware of the medium surrounding it. We, in our sound-filled environment, often do not consider what lies beyond our perception. This leads us to wonder, what other truths about the cosmos remain hidden from our senses? Can we even imagine what it would mean to experience the universe as it is, without our limited human interpretation? In this sense, the silence of the Big Bang becomes a symbol of the limitations of human experience. Physics, through its theories and experiments, attempts to unveil the mystery of the universe. But there is always a limit to what we can grasp. It is an invitation to humility, to recognize that there is more to the cosmos than we can hear or see. In contemplating the primordial silence, we confront the reality that there are aspects of our existence that go beyond our understanding. The relationship between silence and existence is also deeply philosophical. If the universe began in absolute silence, what does that tell us about our own lives and their meaning? The quest for answers to profound questions about the purpose of life, humanity's place in the cosmos, and the nature of time becomes even more relevant. Silence can be seen as a blank canvas, a space where possibilities are infinite, where everything that exists today was once just an idea. Exploring these philosophical implications leads us to question how our beliefs and perceptions of the cosmos influence our daily lives. The silence of the Big Bang can be compared to moments of introspection in our own lives. Those instances when we find ourselves at peace, away from the noise of the world. In those moments, like at the birth of the universe, we can begin to hear the voice of our own existence, to understand who we are in relation to our surroundings. In this way, silence becomes more than just an absence of sound. It transforms into a space for reflection and contemplation, just as the universe has evolved from its silent beginning into a cosmic symphony of stars and galaxies. Our lives can also evolve from those moments of calm, where self-knowledge and connection to the whole become visible. The notion that the Big Bang was silent also challenges us to think about how we communicate our ideas and emotions. In a world that often values noise and activity, silence can be underestimated. However, in that silence may lie the very essence of authentic communication. Just as the universe expanded from its original silence, we can also learn to expand our own voices from a place of calm and reflection. Ultimately, the absence of sound in the Big Bang offers us a unique perspective on our existence. It invites us to contemplate the vastness of the cosmos and our small yet significant part in it. This primordial silence, rather than being a void, can be seen as an invitation to explore and understand more about ourselves and our place in the universe. Above all, the silence of the Big Bang is a reminder that in the pursuit of knowledge, sometimes it is necessary to pause and listen, not only to the sounds around us, but also to the silence that surrounds us and ultimately connects us to the cosmos. In that silence, we can find answers to the deepest questions of our lives and perhaps discover that we are part of a much larger story than we ever imagined. In a corner of the vast universe, scientists are on a fascinating quest to understand how sound, that vibration that brings our world to life, relates to the cosmos. The question that arises is intriguing. Can we really hear the universe? As technology advances, new doors open to explore sound in space. But what does this mean for our understanding of the cosmos and the Big Bang? First, let's consider how the modern era of science is equipped to investigate what once seemed impossible. With advanced telescopes, space probes, and computer simulations, scientists are developing innovative methods to listen to the universe. But how does this listening translate into something understandable for us? Essentially, it's about converting data into sounds that we can interpret. Imagine it as being a translator of an unknown language, where each frequency and vibration tells a story. Astrophysics is beginning to approach sound in a completely new way. Did you know that scientists can convert gravitational waves, those ripples in the fabric of space-time, into sound? When two black holes collide, they release unimaginable energy, and that energy can be translated into an audible frequency. Thus, the universe becomes an immense cosmic symphony, where each cataclysmic event is a note in a universal score. Moreover, the study of sound waves in space is not limited to events like explosions or collisions. Research extends to how stars are born and die. Can you imagine what a forming star sounds like? Astronomers are beginning to use data on pressure and temperature to recreate sounds that can give us clues about these processes. Through physics, sound becomes a bridge that connects what we see with what we can hear. As we move into the future, the possibility of detecting cosmic sounds becomes more tangible. Imagine being able to hear the cosmic background radiation, that echo of the Big Bang that still resonates in the universe. With emerging technologies such as interferometers and other sophisticated devices, scientists are honing their ability to capture these sounds, creating a symphony of events that tells us the story of the universe. What about research on sound on other planets? The exploration of Mars, for example, has allowed scientists to study how sound behaves in a different atmosphere. Did you know that sound travels slower on Mars than on Earth? This opens a new field of study on how sound can change depending on the environment, allowing us to better understand not only our planet but also other worlds. And it doesn't stop there. Sound waves can also help us understand phenomena like the northern lights. When charged particles from the sun interact with the Earth's atmosphere, they generate sounds that are sometimes picked up by special microphones. Thus, the study of sound intertwines with space weather, opening new avenues to understand the dynamics of climate in the cosmos. It's fascinating to think that through sound we can gain information about the composition of stars, the structure of galaxies, and even the behavior of dark matter. What else could we discover if we continue exploring this connection? The acoustics of the universe not only provide us with a new way to view the cosmos, but also challenge us to rethink our relationship with it. Human curiosity is insatiable. Each discovery leads us to new questions. What will it mean for us as a species to be able to hear the universe in its entirety? The idea that sound can be a tool for understanding the unknown is exciting. It invites us to imagine a future in which the cosmos is not just a place we observe, but one we can also hear. As space exploration advances, it is essential to reflect on what it truly means to listen to the universe. It's not just about sound waves, but about interpreting the information that these waves provide us. The science of sound in space is in its infancy, and each advance brings us closer to the possibility of interpreting the language of the cosmos. On this journey, it is crucial to remember that each discovery opens new doors. When we think about the future, what possibilities await us? Perhaps one day, instead of silently observing the starry sky, we can enjoy a cosmic symphony that tells us the story of the universe. In the meantime, science continues its work, unraveling the mysteries of what it means to live in a universe where sound and silence coexist. Ultimately, the exploration of sound in the cosmos not only offers us answers about the Big Bang, but also invites us to question our own existence in this vast universe. Each new discovery is a reminder that the silence of the Big Bang is not an end, but a starting point for a symphony yet to be discovered. The silence of the Big Bang leads us to explore one of the most intriguing questions in physics. Why did the universe begin in complete silence? To understand this concept, it is helpful to think about how sounds work in our daily lives. When we hear thunder in the distance, what we perceive is the vibration of the air that travels from the place where the sound is produced. But what happens in the vacuum of space? The answer is that there is nothing to carry those vibrations. Essentially, sound needs a medium, whether it be air, water, or a solid, to travel. Without a medium, sound simply cannot exist. Some natural phenomena can help illustrate this concept. Think about what happens during an explosion in space. On Earth, an explosion is accompanied by a deafening roar, but in the vacuum of space, that same event would be completely silent. Imagine being in a place where everything is happening, but you can't hear anything. This is because in space, there are no air molecules to transmit sound. This idea is fascinating. The same event can be noisy in one environment and completely silent in another. Another example we could consider is that of volcanoes on Earth. When a volcano erupts, the sound it produces can be terrifying. However, if we imagine a similar eruption in space, the sound we would normally associate with such an event would fade away in the vacuum. The difference between these two contexts helps us appreciate how the presence or absence of a medium affects our experience of sound. The comparison with other phenomena in the vacuum also reveals more about the nature of sound. Imagine a lighthouse in the midst of a storm. The waves crash against the rocks, the wind roars, and the gales howl. All of this creates a symphony of sounds. But if that same storm were to occur in space, where there is no water or air, the scene would be completely different. The waves could not crash, and the winds could not howl. Everything would remain in absolute silence, a reminder that sound is an experience intimately linked to our environment. And regarding explosions, on Earth we can hear the sound of a bomb exploding, but in space that same explosion would become a silent event. This does not mean that the event is not happening, it simply means we do not have the ability to hear it. Thus, the absence of sound in the vacuum becomes a phenomenon that highlights the importance of the medium in sound production. The nature of the vacuum can also be compared to the silence we sometimes feel in moments of deep reflection. Have you ever been in a quiet place where the only sound you heard was the beating of your own heart? That silence can be overwhelming, but it is also a space where thoughts can be heard more clearly. In the context of the universe, the silence of the Big Bang represents a space where there were no thoughts, no vibrations, no sounds, just a vast emptiness to explore. When talking about the silence of the Big Bang, we cannot overlook the extremely different conditions of those early moments of the universe. As the universe began to expand, the conditions were so extreme that any sound, if it had existed, would have been inaudible to any conscious being. Imagine an ocean of hot, dense plasma where sound could theoretically exist, yet there is still no one to hear it. Therefore, silence becomes a fascinating concept. The relationship between sound and silence becomes even more complex when we consider that in other phenomena, such as supernova explosions, sound also behaves differently. In our environment, a supernova would be heard as a powerful roar. However, in the vacuum of space, that sound dissipates into silence. Reflecting on this, we find that silence can be both a void and an opportunity, a space that invites reflection and exploration. The nature of sound is also related to other phenomena like echoes. On Earth, when you shout in a canyon, the sound bounces back to you, creating a unique auditory experience. But in the vacuum of space, there is no echo because there is nothing to bounce back. This idea of the lack of echo in a mediumless environment is a powerful metaphor for understanding the silence of the Big Bang. A moment when there was nothing to bounce back, nothing that could be heard. In conclusion, the silence of the Big Bang invites us to contemplate our own existence and the nature of the universe. The absence of sound in that first cosmic moment highlights not only the importance of a medium for sound production, but also the wonder of the universe itself. Just as the sounds of nature connect us to our environment, the silence of the Big Bang connects us to the vastness of the cosmos, reminding us that sometimes silence can be as powerful as sound.